Right. Hi, everybody. This is a deeply trivial first. This is the very first time I've ever made a video for one of my posts, and I'm hoping it won't be the last. We'll see how this goes. I've thought about doing this before now. Last year, when I blogged through the A to Z of statistics, I thought about doing videos for some of the posts because some of the concepts I was talking about were a little bit more complicated. And I thought it might be nicer to just kind of sit down and conversationally just talk about these concepts as opposed to writing about them. The reason that I didn't do that is because I know that when I'm really excited about something and when I am geeking out about something, I have a tendency to just talk and go on for a while. And I was a little concerned that some of those videos would get kind of long. So that's why I ultimately decided to write, because I can be a little bit more concise when I write. The reason that I've decided to do a video today, though, is because for today's Statistics Sunday post, I wanted to go through the output from the confirmatory factor analysis from the F is for factor analysis post and talk about how I would interpret that output and what the different things mean. And I tried to think about the best way to do that. I thought about taking the screenshots of the output and adding some markup and circling values that are important and then adding in some narrative to explain things. But I was worried that that would get kind of complicated and difficult to follow. So I thought it would actually be easier if I just sat down and just ran the analysis and talked through how I did it. So I'm going to try to keep this video from becoming very long. And I think because I have a very specific goal in mind, that'll keep me from going too far off track. Okay, so we'll go ahead and open up RStudio, which is where I conduct all of my analyses. I'm a big fan of RStudio. I think it's really easy to use, and I prefer it anytime I use R for analysis. I'm using RStudio. And I've created a syntax file where I've just copied and pasted the code that I included for the F is for factor analysis post. So there really isn't anything new here. There's a couple of things that I've added, and I'll explain why I did that in just a moment. So first up, I'm going to go through the single factor analysis that I conducted using the satisfaction with life scale data. So this is from the Diener satisfaction with life scale, which has been around since the 80s. It's been very well studied. It's been translated into different languages. It's been used quite a bit to study satisfaction with life and related concepts. So that's part of the reason that I have no problem with just using this for a blog post example, is because this scale has been studied and published about to death, and there's no way that I'm going to be able to get a publication out of these data because I didn't do anything groundbreaking. There's really nothing new here. In academia, there's this great concept called least publishable unit, which is basically how small of a chunk can you chop off of a data set and get a publication out of it. It's kind of the minimal group paradigm applied to data. And I honestly think I've gotten all the publications out of this data set that I'm going to. I don't think there are any more LPUs here. There are, however, many least bloggable units, LBUs, and I think I'm going to start measuring my data sets by how many blog posts I can get out of them, because I've already written a lot of blog posts about this data set, and I'm going to be writing a lot more in the future, so I've got a lot of LBUs here I can track. So we'll go ahead and load up our data set. This is just the same one that we've been using. And I'm also going to specifically create a data frame that just contains the satisfaction with life items. And I'm mostly doing that so I don't have to dig through a lot of output. Okay. So we'll go ahead and load our model. So this is just a single factor model with the factor being satisfaction with life and 5 indicators, which are the 5 items from the satisfaction with life scale. And then I'm going to load lavaan, which is the SEM program that SEM library that I use in R. And then we also went ahead and fit our SEM objects. So Let's take a look at our output. Okay, so SEM is an iterative technique. It takes the model that you specify and basically puts together what the data should look like if that model were reality, if that model perfectly explained your data. And then it has the observed data, the data that you actually found. So it generates some starting values, and then it goes back and forth, futzing with those starting values and trying to come up with a final estimate, a final solution that both fits the model and also fits your data. And so we can see here, lavaan and other SEM programs tell you how many times the program had to iterate before it finally converged on a solution. So in this case, it iterated 24 times um, from that starting value until it finally gave us our final estimates. So the first thing that I would take a look at is I would examine fit measures. And the very first fit measure that I would examine is chi-square. So chi-square, you might remember from a post I wrote about chi-square, is a goodness of fit test. And so in this case, the goodness of fit that you're examining is how different your observed data are, the data that you collected, from what your data would look like if it perfectly fit the model, if the model was reality. And so in this case, minimum function test statistic, this is your chi-square. We actually want this to be non-significant. We want our model to fit our data well. So we want the difference between our observed data and our model specified data to be as small as possible. So this is significant. Chi-square is actually biased to be significant. So this is not uncommon. In fact, this happens quite a bit that you might have a significant chi-square, but you still might have a good model. So also want to look here, number of observations 257. Just make sure that that matches the number of people you have in your sample. In this case, it does. You might notice that the chi-square associated with the degrees of freedom associated with our chi-square is 5. So if you remember back from the degrees of freedom posts, I talked about how degrees of freedom is based on the number of inputs that you give the program. The number of inputs is sometimes, for some analyses, based on the number of people or the number of data points in your sample, but SEM is an analysis of covariance. So your inputs are actually the number of pieces of covariance you give it. So that's where your degrees of freedom are figured out. It's the number of covariances, which I'll show you in just a minute, minus the number of things that you're asking the program to estimate. So covariance is a combination of correlation and variance. So correlation, of course, is a measure of the strength of the relationship between two variables, and variance is just the squared standard deviation. For covariance, it's the standard deviation of one item times the standard deviation of the other times the correlation between the two. So let me show you a covariance matrix. So a covariance matrix, like a correlation matrix, is symmetrical. The values below the diagonal are equal to the values above the diagonal. So we're just going to ignore these values above the diagonal. Along the diagonal, these are the variances. So the variance of the first item of life satisfaction, the variance of the second item, and so on. And then the covariances, these values off the diagonal, like I said, is the standard deviation of LS1 times the standard deviation of LS2 times the correlation. So I can even show you how that's figured. So the correlation between the first and second items is 0.689. That's a pretty high correlation. We would expect items on the same measure to correlate highly with each other. And then if we look at our standard deviations, so standard deviation 1.63 for the first one, 1.58, and a correlation of 0.689. So (1.774451) within rounding error, that's our covariance. So the number of inputs that we gave the program is based on this guy and actually just the diagonal and below because these values are the same. So we don't have 257 degrees of freedom to start with. We have less than that. We have the number of covariances that we're giving it here. So you can run into the problem sometimes when you conduct structural equation modeling where you run out of degrees of freedom very quickly because your degrees of freedom are determined by the covariances, the number of variables that you're giving it basically, and the number of potential relationships with other variables. So you can run out of degrees of freedom and have a model with 0 degrees of freedom, which is what we call a saturated model. When your model is saturated, it doesn't compute any fit statistics for you. It just tells you that the fit is perfect because it's out of information. It can't estimate anymore. So personally, I stay away from saturated models, and there are different things that you can do. You can drop paths. You can add in other variables if it makes sense. There's some disagreement. Some people say that a saturated model is fine, but there's so little information you can get about a saturated model that it really doesn't tell you much, and you could have a really bad model and not know it because it won't generate any fit measures for you. So the first fit measure you look at is your chi-square. Chi-square is biased to be significant, so one thing that people will do is they'll also look at what's called the normed chi-square, which is your chi-square divided by your degrees of freedom. So that is 26.76 divided by 5. There's some disagreement on what your normed chi-square should be, what should be a cutoff for that. I've heard some people say 2, I've heard some people say 4, I've heard 5. A normed chi-square is essentially a chi-square with 1 degree of freedom because you're dividing your chi-square by degrees of freedom, which means you're also dividing your degrees of freedom by degrees of freedom, which is equal to 1. So personally, I use the critical value from the chi-square table for a chi-square with 1 degree of freedom, which is 3.841. So even our normed chi-square here is higher than it should be. It's higher than I think it should be and higher than many people think it should be. So this is an indicator that we might not have a good model here. Sorry, Diener. And I actually should have run this one because this gives me all of my fit measures. So like I said, the very first place I look is at the fit measures because if you have a badly fitting model, the other stuff doesn't really mean anything. The model is bad, and you should go back to the drawing board and come up with a better model. All right. So there's some different pieces of information that this program gives you. Lavaan actually gives you less than some other SEM programs, and that's a good thing because some SEM programs give you a ridiculous number of fit measures, and there are really only 5 or 6 that I actually look at. And so lavaan actually mostly gives the ones that I look at. And these are the ones that are recommended in the literature. So first of all, you have these 2 things here, comparative fit index and the Tucker-Lewis index. I'm going to write a blog post later on where I actually go through and talk about what these different fit measures mean and how they're determined. The only thing that I'll say for now is that these 2 are based off of your chi-square, and you want them to be greater than or equal to 0.9. Closer to 1 is better. So in this case, both of these are greater than 0.9. So these would indicate good fit. This is something that you'll run into with SEM is that you look at multiple fit indices because they'll tell you different things, and sometimes they might contradict each other. So you kind of have to figure out where to go with that. And if only one fit measure is telling me that a model is bad and the rest are telling me that the model is good, obviously I will give all of that information in a publication or presentation. But if most of them are saying that the model is good, then I tend to conclude that the model is good. So far we have 2, the chi-square and the normed chi-square, both telling us that this is a poor fitting model, and we have a couple here, are fit indices that are saying that this is an acceptable model. AIC is something that I look at when I'm comparing two different models to each other, and when those models are so different that they can't be considered nested. And I'm going to write a future blog post where I talk about nested versus non-nested models. But when models are non-nested, which means that they have different indicators or they have a different factor structure, you would compare AIC to each other, and a smaller AIC is better. Some people also like the BIC. They're both determined in a very similar way, and they tend to give you pretty similar results. So then the two other things that I look at is the RMSEA, the root mean square error of approximation, and the SRMR, the standardized root mean square. Both of these are based off of differences between your observed data and what the data would look like if it fit the model. Like I said, I'm going to write a blog post later on where I actually give you the nitty-gritty of what these different things mean, because those are more complex concepts. But these are two things that I look at, and the cutoffs that I use for RMSEA, I use 0.07. So we want it to be less than or equal to 0.07. And for SRMR, I tend to use 0.08. Sometimes I'll see people recommend less than or equal to 0.05, and there are different arguments for why different values might be better. Once again, we're having a contradiction. Our SRMR is telling us that this is a good model, and our RMSEA is telling us this is a bad model. And actually, of all the fit measures, the one that I probably pay attention to the most is the RMSEA. And if it's greater than 0.1, I tend to say this model is junk and I need to start over. So, sorry, Diener, it looks like this might not actually be a good model. Or maybe it's just bad data. We'll just say it's bad data. Anyway, so because these fit indices are telling you that this isn't a great model, I normally wouldn't go on and look at my parameter estimates, but for the sake of demonstration, I'm going to do that. So let's pretend that all of these said the model is beautiful and that it's good fit, and we'll keep moving. So first of all, this first section where it says latent variables is giving you your factor loadings, the loadings of each of the indicators onto the factor. Now, your observed variables have a metric. They have, in this case, the scale that people use to respond to them, which I believe is a scale from 1 to 7. There's strength of agreement with different statements. So each of these variables has a metric already. Satisfaction with life is a latent variable. It doesn't have a metric. It has to be assigned one. And so the way that SEM programs does this is that one of the indicators is fixed with a factor loading of 1. This gives our latent variable the same metric as that indicator. What this means is that it's not giving you standard error and it's not giving you a significance test for this. So what people recommend is either to fix the first indicator onto the factor with a factor loading of 1, which is the default for most programs, or to fix the indicator that you think is the strongest measure of that factor at 1. And then the other factor loadings are estimated based on that. It looks like in this case that this one, if it wasn't our strongest, was one of our strongest. So using the first one was fine. This is one reason why you also want to ask for your standardized factor loadings, because it does give you that even for indicators that have a factor loading fixed at 1. So it conducts a z-test, and we want these to be significant. This means that these indicators are significantly related to this factor that we're trying to measure. So unlike chi-square that we want to be non-significant, indicators we want to be significant. And the next up, variances. Variance is the leftover variation in that indicator or factor not accounted for by the model. So the variance for LS1, for example, is the variance left over in the first item after we've accounted for the variance explained by the factor. So we actually want our variances to be non-significant, theoretically. We want each of our indicators to be really strong measures of the factor that we're trying to measure, meaning that there would be little to no variance left over. Because up here, we're looking at systematic variance, variance explained by this factor. Down here, we're looking at error variance, leftover variance, after we've taken out the systematic. It's very, very unlikely to have a factor analysis where you have non-significant variances because there are any number of things that can affect people's responses to an item, not just the thing that you're measuring. So while we would want these variances to be non-significant, they're pretty much always going to be significant. There's always going to be leftover variance. Only in a few instances have I conducted a structural equation model where I've had non-significant variances, and you kind of do a happy dance when that happens because it is really unusual. And then once again, your variance and your factor is leftover variation in this concept of satisfaction with life after you've partialed out the variance accounted for by the model, accounted for by the indicators that you gave it. Now, your standardized loadings work kind of in a similar way as the betas, the standardized regression coefficients that I talked about in the B is for beta post. These allow you to compare your variables to each other and compare the strength of their relationship with the factor. So standardized loadings, when we want to look at the standard all, standardized loadings range from -1 to +1. They're basically like correlations, the strength of the relationship between LS1 and satisfaction with life standardized. So as we can see, and so we can compare these values to each other, as we can see, the third item seems to be the best indicator of satisfaction with life. The second item is the second strongest indicator, and the first item is the third strongest indicator. And we can also see this down here reflected in our variance. This is that leftover variation after the variation accounted for by our factor model has been partialed out. So we can see that this is the best indicator and it has the least amount of variance left over. So that's the relationship between these two indicators. All right. So, like I said, future post where I'll actually talk about going through and where these different indicators come from, what they mean. Like I said, they're based on your chi-square. And so look for a future post on that. So now, just for fun, let's run that ruminative response scale model again and go through that output. Okay. As we can see, it's still running and it's done. Let's take a look at our summary. This output is going to be longer because this is a much longer scale. There are 22 items as opposed to 5. And we also have some different things in here. So I went ahead and requested standardized factor loadings and variances, and also requested my fit measures. So once again, number of observations is correct, 257. Degrees of freedom is much higher in this case because we had these 22 variables that we were dealing with. So we gave it a lot of pieces of variances and covariances. We still have a very significant chi-square, but if I divide these two, 600.311 divided by 206, we actually have a non-significant normed chi-square, 2.91. So like I said, once again, I personally compare to chi-square for 1 degree of freedom, which is 3.841. I've had many people argue with me on that, but nobody really seems to have a set answer to that. As with so many things in statistics, there's a lot of debate and not necessarily clear answers. So that's good, but our CFI and our TLI are less than 0.9. So these would tell me that this might not necessarily be a good model. Our RMSEA is greater than 0.07. It's less than 0.1, which makes me happy, but it's still greater than that 0.07. So this tells me that this might not be a good model. SRMR is less than that 0.08. But once again, we've got 3 pieces of information here, CFI, TLI, and RMSEA, telling me that this might not be the best model for these data. All right, so our factor loadings, once again, the same thing. We have 3 factors here. Each of these factors needs a metric assigned, which means that they each have one indicator that is fixed at 1. All of them are loading significantly, which is good, which is what we would expect. And then we've also, by default, allowed our 3 factors to correlate with each other, because since they're all on the same measure, even though they're measuring independent constructs, they're all on the same measure. It makes sense that they should all be related to each other. I talked briefly in the F is for factor analysis post about setting orthogonal equals true, which means not allowing the factors to correlate. And this you do for hypothesis testing to see if these factors are so strongly correlated that by telling the program, no, do not let them correlate, the fit of the model actually gets worse. That's evidence that backs up this idea that they're all significantly correlated with each other. All of our covariances are also significant, which also does tell us that they're significantly correlated with each other. And then once again, we look at our variances and we see that there's significant variance left over after we've accounted for the variance for the model. All right, so last step, let's go ahead and try running this higher order model. So this is the one that has our 3 factors, but then has the 3 factors loading onto a second order or a higher order factor. So let's try running that. Go ahead and fit our model and request. So let's see what happens. We gave it the same data, we gave it the same number of indicators. It makes sense, once again, that our chi-square is going to be the same. What this tells us is that while this model might not necessarily fit better, it doesn't fit any worse when we add in the second order factor. But these guys are still less than 0.9. RMSEA, everything is still about the same. This model doesn't really give us anything new. It doesn't necessarily fix the problems that we have with this model and how the model relates to the data that we collected. One thing that I should mention, because I don't want to completely throw shade at the ruminative response scale, I think it's a really good scale. This is a measure of rumination, which is clinical concept. And these data were collected in a non-clinical sample. So this might not necessarily be the best measure to be using in this type of population. All right, so I'm going to go ahead and wrap that up here. Like I said, look for some future posts where I actually talk about these different fit indices and what they mean, because I don't want this video to get any longer than it probably already is. And I think those concepts will be easier for me to write about as opposed to talk about. So thank you for watching this video. Hopefully you liked it. If you are not already a fan of the Deeply Trivial Facebook page, head on over to facebook.com/deeplytrivial, all one word, and give us a like, and you'll get updates when there are new posts. If you're on Twitter, you can find us at Deeply Trivial, once again, all one word. And of course, the website is deeplytrivial.com. So thank you for watching. Hopefully you enjoyed this video and hopefully you learned something new.